Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on filter design. Okay, so this video in fact is a improvised one. Once again, thank you so much for your valuable suggestion. Okay, so because of your suggestion, I have decided to redo this video. Okay, so this video will have two portions. Okay, the first portion will be on the theory aspect. The next portion will be the example, okay, to show it to you how can we actually design a bandpass filter with connecting line and also the lambda overflow shunt short circuit stub. So basically, this will be the objective of this video. This will be the part 18 series discussion on filter design. So guys, if you're keen to know more about filter design, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on filter design. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by pressing the like button. So guys, give me a few seconds. Help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's come to the theory discussion. How can we actually have a bandpass filter together with the shunt short circuit stub and also the connecting line? Okay, so over here you can see that a bandpass filter can be easily created when we actually use this shunt lambda over 4 quarter wavelength short circuit stub together with the connecting line. Okay, so how they achieve is basically they using this impedance transformation property of a transmission line. And because of the resonant behavior of the stub, so therefore we have a bandpass filter characteristics. Okay, so basically you can see from here. Okay, so the line that are so-called vertical, these are what we call the lambda over 4 short circuit stub. Okay, so basically you can see that this is short circuit. So therefore we call this as a short circuit stub. We call this lambda over 4 because the length of the transmission line is actually lambda over 4. This is what we call the connecting line. Okay, so basically you can see that the connecting line also play a role in terms of designing the bandpass filter. Okay, so later on you will see that both the connecting line and the shunt short circuit stub actually involve design rules to have this bandpass filter characteristics. Let's take a closer look on the shunt short circuit stub. How can we actually have a pass band characteristics? Okay, by having the length of quarter wavelength, okay, short circuit stub. A lambda over 4 short circuit stub behaves as an open circuit at its resonant frequency. Okay, so this is because the short circuit at the end of the stub is actually transformed into an open circuit at the input due to the quarter wavelength impedance inversion. Okay, so what does this mean? Okay, let's take a look on these two diagrams. Let's focus the one on the left first. Okay, so this is what it means here. So the length of the transmission line is quarter wavelength. And over here, you can see that it's a short circuit. So if you still remember, okay, once you have this short circuit, if you turn onto the Smith chart, okay, if let's say the length is actually quarter wavelength, this will become an open circuit. This is a short circuit. After lambda over 4, this part become an open circuit. Okay, so let's imagine this. Let's say the signal of 2 gigahertz, okay, basically pass from, let's say, whether are they able to pass from port 1 to port 2. If they are able to pass to port 2, which means that this 2 gigahertz is actually able to pass from these characteristics here. Okay, so over here, okay, this is a short circuit, it become an open circuit. Okay, let's say we design the rule based on 2 gigahertz. So once the 2 gigahertz signal come over here, this become an open circuit. So therefore, all the signal will be going to port 2. So from here, you can see that if we have this so-called quarter wavelength with respect to 2 gigahertz, then 2 gigahertz will be able to pass from port 1 to port 2. While at the another example here, So instead of short circuit, it become a open circuit. So again, based on the quarter wavelength, so this is open, this become short circuit. So let's say we design this quarter wavelength based on 2 gigahertz again. So the signal of 2 gigahertz come over here. So when they actually touch base here, remember this is open, it become a short circuit. So the signal actually will travel this path. So you can imagine that 2 gigahertz will not be able to reach port 2. Okay, so therefore, it actually has a so-called a band stop center at 2 gigahertz. So therefore, with this, you can imagine that we will be able to have a bandpass filter. Okay, basically, if we control the center frequency of the bandpass filter, okay, basically, we will have this frequency response. Okay, so basically, this is why okay, we actually can implement a bandpass filter with a quarter wavelength short circuit stub. At frequency away from the resonant, the stub actually present a reactive impedance, either inductive or capacitive, which affect the transmission characteristics of the filter. Okay, so we are going to take a closer look later on this. But over here, okay, the key essential is basically if this is short circuit, it become open circuit, okay, which means that the original signal that let's say we design for 2 gigahertz, they will be able to pass from port 1 to port 2. So therefore, this will be a bandpass filter at 2 gigahertz. But if we have this kind of configuration, okay, so we have this open circuit, it become a short circuit over here. So the 2 gigahertz signal, okay, will be so-called travel this path and nothing will reach port 2. So therefore, we have this band stop at this 2 gigahertz. Okay, so basically, as I mentioned, the 2 gigahertz will be the resonant frequency. So basically, with this, okay, basically this form the fundamental design of a bandpass filter. Okay, so as long as you make sure that the length of the transmission line is at the center point of the bandpass filter, you will be able to achieve this bandpass filter characteristics. Next, let's move on to the connecting line. Okay, so the connecting lines, which is in between the stubs, they actually provide the necessary phase delay and also impedance matching to ensure proper signal transmission at the desired passband frequency. Okay, so this line also help in creating the desired frequency response by interacting with the stub impedance characteristics. Okay, so these are the connecting line. Okay, so the connecting line, basically what they do is basically they do a matching. Okay, so remember if we have a proper matching, okay, we are able to send a signal from port 1 to port 2. So basically in short, later on you will see that the design rule is basically fall on two parts. One is on the design on the connecting line, another one is on the design of the shunt short circuit stub. Then we can have the overall achievement of bandpass filter. Okay, so basically we will take a look on this again. Coming to the number 3, okay, how can we actually have this bandpass filter design? Okay, by placing multiple lambda over 4 short circuit stub at regular interval along a transmission line, you actually create a structure that selectively allows signal within a specific frequency range, okay, or the passband to pass while antenating signal outside this range. Okay, you can see over here, I actually have these 3 shunt short circuit stub. Okay, so basically this is what I mean. If we properly put them in at a regular interval, we are able to have this bandpass filter characteristics. The stub act as a resonator and their spacing and dimension actually determine the center frequency and also the bandwidth of the filter. The connecting line ensure proper coupling between the stub and maintain the desired impedance matching across the passband. Okay, so with this, I think you have a better idea how this so-called structure can have a bandpass filter characteristics. Coming to the working principle, okay, at the resonant frequency, okay, which is the center frequency of the passband, okay, let's say this part here, the center frequency of the passband, lambda over 4 stub actually present a high impedance, okay, which is the open circuit, as I illustrated earlier on, to the transmission line, allow signal to pass through with minimum reflection. At frequency below or above the resonant frequency, the stub actually introduce some form of mismatch and reflection. Therefore, they actually antenate the signal and they actually create the stop band region. Okay, so basically this is what I mentioned earlier on. So let's say this is at 2 gigahertz, I will be able to pass through from port 1 to port 2. Okay, the rest of the frequency, they actually have some form of mismatch and some form of reflection. So therefore, not all the signal will be able to reach the port 2. So therefore, with this, we actually can have this pass band characteristics as shown in this diagram here. Coming to the design step, okay, so later on I will have an example, okay, but over here, let's quickly understand what are the design steps to implement bandpass filter with shunt short circuit stub. Firstly, okay, we need to determine the center frequency. Okay, so this is the frequency at which the stub are lambda over 4 long. Okay, so basically the length of this so-called shunt short circuit stub actually will be based on the center frequency of the bandpass filter. Okay, so this you need to be very careful. Calculate the stub length. Okay, so the physical length of each stub is actually lambda over 4 at f naught. Okay, where lambda over g is the guided wavelength. Choose the number of stub. Okay, so over here you can see that the number of stub is 3. Okay, so the more the stub, okay, this actually result in a sharper transition between the pass band and stop band. Okay, which means that your skirt will be steeper the more number of stub that you actually implement. Okay, so in order to have a higher selectivity, you can consider to put more stub. So basically, this is what it means. Okay, optimize the connecting line. The length and impedance of the connecting line are adjusted to achieve the desired bandwidth and also the impedance matching. Okay, so basically these are all the design steps, okay, to design the bandpass filter. Come to the advantage. Okay, so when we actually implement this bandpass filter, okay, with the connecting line plus the shunt short circuit stub, the key advantage is this is relatively simple. Okay, so later on you will see how simple it is to design this bandpass filter. Next is basically you are also using this distribute element, okay, rather than lump element, okay, which means the L and C. Okay, so they are actually suitable for high frequency application. They can be easily implemented, okay, in a planar technology like microstrip line or strip line. Okay, so but this video I will concentrate on the microstrip line. Coming to the limitation, okay, the filter performance is actually very sensitive to manufacturing tolerance. The physical size of the filter can be large at lower frequency, okay, due to the lambda over 4 requirement. Okay, so basically the size of the filter must be at least this size. Okay, so this size, if let's say cannot meet your so-called your design rules, then you probably need to use another method to design this bandpass filter. Hence, let's do a quick discussion. Okay, by carefully design the stub and the connecting line, you can create a bandpass filter with the desired center frequency, controlling the bandwidth also, and the rejection characteristics, okay, based on the number of so-called shunt short circuit stub that you actually can choose. Okay, so before we come into the discussion on the formula, okay, so again, okay, if you have learned something from this video, please consider to like this video. For those who are new, and if you have learned something, please consider to subscribe and turn on your notification bell. Let's start the design. Okay, so basically, let's quickly do a quick recall. What is connecting line and what is shunt short circuit stub? Okay, so over here, you can see that the line that are so-called vertical, okay, they are actually the shunt short circuit stub. The line that are horizontal, they are actually called the connecting line. Okay, so basically, we need to understand this, okay, because the design rule actually fall on these two, okay, the connecting line and also the shunt short circuit stub. Let's come to the formulas that we actually need to design this bandpass filter. Okay, so this is the first step of formula here. Okay, second step is basically to design the connecting line. Again, you can see a series of formula. Okay, so this formula will be implemented on the first one. This formula is actually implemented on the last stage here. Okay, so whatever that is in between will be using this formula. Over here, you can see that this is the first one, so I will use this formula. This will be the last one, so again, I will use this formula. Anything in between, I will be using this formula here. Okay, so we will take a closer look. But over here, let's just quickly discuss the formula that is actually required to design this bandpass filter. And then step number 3 basically will indicate the value of the so-called the admittance scale on all these connecting line. Okay, so over here with this, you actually finish the design of the connecting line. Okay, so again, later on, I will have an example to show it to you how can we actually obtain all this number. Next will be on the shunt short circuit stub, okay, which is all the vertical line here. Okay, again, okay, let's quickly understand. These are for the first stage. These are for the last stage. Okay, and then this formula is basically anything that is in between. Okay, keep this in mind. Okay, always have a rules to design the first and the last stage. Then the center, you can actually use this step number 4 to compute. Okay, so this is purely on the first one. This will be purely on the last one. And this will be so-called in between the first and the last one. Okay, one thing before I continue the discussion. Okay, so the filter design, most of the time, we actually want to so-called design symmetric. Okay, so which means that if let's say we put a mirror over here, okay, so what I can conclude is this and this will be equal, this and this will be equal, Y1 and Y5 will be equal, Y2 and Y4 will be equal, and Y3 you need to so-called separately calculate it. Okay, so basically in short, what I need to do is Y12 okay, will be basically equals to Y45, Y23 will be equals to Y34, Y1 will be equals to Y5, Y2 will be equals to Y4, and then we have this Y3 here. Okay, so once you have all this, okay, so basically these are all the calculation on the shunt short circuit stub. Okay, so basically after you have calculated using this formula, you will be able to get all the admittance of the shunt short circuit stub. Okay, so with this, let's start by the design. Okay, so firstly, design a bandpass filter using microstrip line with specification as following. Okay, so the fifth order, which means that I'm going to have 5 shunt short circuit stub. Okay, so basically this is the first criteria. A fractional bandwidth of 0.5, okay, at a middle band of f naught equals to 2 gigahertz. Okay, so the center of the bandpass filter will be 2 gigahertz, and we are going to use 0.1 dB pass band ripple characteristics here. Okay, so basically this chart is actually the 0.1 dB pass band ripple characteristics. Okay, from this table here, I will be able to obtain okay the G0 to G6, okay, so 1 and 1 over here, and then this G1 is 1.1468 here. Again, you can see that they are actually symmetric. So therefore, this G1 and G5, they are 1.1468 here. And so-called G2 and G4, they are the same. So they are actually having this 1.3712. Same for G3, which is 1.975. Okay, so basically, I guess you know how to get this number. You just need to refer to the table. N is equals to 5. So therefore, I'll look into the N equals to 5. And basically, I will have all this G term here. So next, okay, this is the step number 1. This is how we calculate on this value here. So let's do quickly a discussion. This is pi over 2, 1 minus, this is the fractional bandwidth. Okay, the question given to us is 0.5. This is how big the bandwidth is. So basically the fractional bandwidth is 0.5. So therefore I put a 0.5 here. So if you punch your calculator, okay, I don't foresee that you have issue to get this number, 3 pi over 8. Okay, so basically this will be the step number 1. Step number 2, we are ready to design the connecting line. Okay, so basically we can let the H is equals to 2. Okay, you can see that there is actually a H term here. Okay, so this number can be any number. Okay, but I will strongly suggest you guys to keep it within like 1.5 to let's say 3. Okay, so basically this number will be able to control the impedance. Okay, so we don't want the so-called the characteristics impedance of the transmission line to be too big or too small. So therefore, typically, we would like to control this H value. Okay, so as I mentioned, okay, I always like to let H is equals to 2 first. Then we will have a better idea how to design this microstrip line. I'll come to this later on. Okay, but always start from this H equals to 2 first. Okay, after that, then you can consider to so-called change this H value in order to optimize the impedance. Okay, so basically, let's say I have a very narrow okay, transmission line, which means high impedance. Then I like to control the H okay, to make sure that this is possible. Okay, so let's come to the step number 2. Okay, as I mentioned earlier on, okay, basically the first one and the last one will have a unique formula to calculate. Okay, so if you use these two, you will actually having the same number because the filter is symmetric. So Y12 will be equals to Y45. Okay, so over here, how can we actually get all this number? Okay, G naught, okay, basically I have put all the G number here. So G naught is equals to 1, okay, as you can see from here. H, as I mentioned to you, I will always use 2. G1 is actually equals to 1.1468, which is here. G2 is actually equals to 1.3712. So from here, I actually achieve 1.293. Okay, coming to the last stage here, which I mentioned earlier on, I need to use this set of formula. Okay, so again, G naught is equals to 1. H, again, I must not change the H value. The H value must be consistent. If I use 2, every calculation, I need to use 2. Okay, so again, G1 is equals to 1.1468 here. G6 is equals to 1, as you can see from here. And then G naught again is equals to 1. G4 is actually equals to 1.3712. So again, if you punch your calculator, you should get this number. Okay, one thing again I like to highlight, because the filter is symmetric, so therefore you can see that these two values should be identical. Okay, so next, okay, I'm ready to calculate the connecting line, the next portion of the connecting line in between the first one and the last one. Okay, so again, because they are symmetric, so therefore I do not want to calculate 2 times. Okay, so basically over here, I will use another set of equation. Okay, so basically this is another set of equation. So this will be calculate the so-called the 2, 3. Okay, so basically you can see that I will rewrite all this equation over here. Say again, H, I will still remain 2. G naught is equals to 1, as you can see from here. Okay, G1 will be 1.1468, as you can see from here. Again, okay, square root, okay, G2, G3. G2, which is 1.3712. G3 is 1.9750. Again, okay, I don't foresee any issue how you can actually obtain this number here. So once you have all this number, okay, we can start to design the connecting line. Okay, so again, these are the formula, okay, to design the connecting line. Okay, so if you use all this number, okay, you should be able to get all this admittance of the connecting line, as you can see from here. Okay, so this is 0.02586 here. Okay, so they are symmetric, and then these two again, they are also sorry, these two things, they are actually symmetric. These two, they are actually symmetric. So therefore, you can see that I have calculated all the admittance of the connecting line. So half of my task I finished. I have calculated the connecting line. So next, I will focus on the shunt short circuit stub. Again, this is the step number 4 formula here. Okay, so basically I have N12, N23, and N34. The rest, because they are symmetric, which I do not want to calculate. Okay, so how can we actually do this? Okay, for example, earlier on we have calculated this J12 Y naught here. If you still remember, this J12 Y naught basically is over here. J12 Y naught here, okay, which is 1.293. Okay, so therefore I actually put this 1.293 over here plus H, which is equals to 2. Again, all this number you should be able to obtain. Okay, so this is the data that I actually calculate early on the step number 1. Okay, make sure you set your calculator to radian mode. Okay, so basically this is what I have calculated on the step number 1. Okay, over here 3 pi over 8. Okay, so therefore I will have this 3 pi over 8 over here. So if you punch your calculator, you should be able to get this number. Okay, same wise for N23 and N34. Okay, so basically I have calculate the shunt short circuit stub. Okay, I have calculate the first one, okay, the second one, and the third one. Okay, so basically this is what I have calculate here. Okay, let's move on. Okay, so let's do a detailed study, okay, to get all these number. As I mentioned earlier on, the first one, I have a standard formula. The last one, again, I will have a standard number to calculate. Okay, so you can use this to do the calculation as shown over here. Okay, so this G naught is equals to 1. Okay, so this Y naught is actually 1 over 50. 1 minus, okay, so basically, as I told you, this will be 2 over 2. Okay, I purposely choose this 2. Okay, because over here 1 minus 1, this whole thing will be stripped off. Okay, this equation whole thing will be stripped off. Then I just need to concentrate on this portion here, which is equal to 0.03525. Okay, so as I mentioned earlier on, Y1 and Y5, they will have the same number. So I don't need to calculate the Y5 value. Okay, so basically I'm done on the first one and on the last one. Okay, so next, okay, I'm going to calculate Y2. Okay, how to calculate Y2 over here? So this is actually the set of formulas, okay, for the so-called something that is actually in between the first one and the last one. You need to use this formula. Okay, so all this value is what I have compute earlier on. Okay, so let me show you to you. So this is Y naught N12. Okay, so basically N12 is basically what you have calculated over here. So N12 is equal to 3.0556. So therefore from here, this is 3.0556 over here. Okay, why not? I think by now you should know it's 1 over 50. So I actually get this number. Okay, N23, again, you can refer to the previous example here, which is 3.0997. So therefore, this is the number. Okay, minus J12Y0. Okay, so basically J12Y0 will be from here, J12Y0 here. J12Y0 is 1.293. Okay, so therefore, I actually have this 1.293 over here. Same for the rest. So basically, I guess with this, you should be able to calculate all the shunt short circuit stuff. So over here with this, you can see that firstly, I have calculated all the connecting line. So next, this few step, I actually also managed to calculate all the shunt short circuit stuff. And basically with this, okay, I will be able to design the microstrip line. Okay, so these are all the value that I have so-called calculate. And then after that, I actually fabricate on a microstrip line. Okay, basically from here, you can see that these are all the so-called VR. Okay, basically they drill to the ground plate so that this can be a so-called the short circuit stuff. Okay, so basically I will have another video to show it to you how can you actually transform from the schematic to the layout of a microstrip line. Okay, I will share the video okay on the description. But over here you can see that I have successfully designed a bandpass filter using microstrip line. This is what we call the connecting line. Okay, so basically this is Y12, this is actually Y23, this is actually Y34, and this is actually Y45. Okay, so this is Y5, this is actually Y4, this is actually Y3, and this is actually Y2, this is actually Y1. Okay, so these are 50 ohm okay, ports here. So with this, okay, I'd like to quickly show you the so-called outcome. Okay, so basically with this, you actually can achieve a bandpass filter. Okay, so basically the filter asks for, the spec actually asks for 2 gigahertz. You can see that I'm able to achieve a 2 gigahertz bandpass filter. Okay, with this, I'd like to end my discussion. Okay, please sub to like and subscribe. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you.